up to this point, as we've been learning about integration, we've really only had our power rule and then our rules for the integrals of trig functions. So we're going to introduce a really powerful and important rule, which is the substitution method or the substitution rule. So just as we use the chain rule when we are differentiating composition functions, when we find the derivative of something that is inside of something else, well, when we do the antiderivative, we're going to break it down first. Okay, so we break that function down into, hey, what might be the inside and what might be the outside. So the substitution rule says that if I have a function per se, so if I'm dealing with the integral of a function of a composition, so this says f of g, right? So if we think about that, then we also need that derivative of the inside. So what we're going to do is we're going to decompose it and break it down in a way such that we can just call it f of u du. We're going to make it simpler using substitution. All right, so let's look at the proof. So let's consider the chain rule for derivatives, okay? So we understand the chain rule, and when we're dealing with a composition function, f of g of x, and this is the antiderivative, right? This represents the antiderivative of some composition function, f of g of x times g prime of x. And we could check that. I can say I know this because if I were to take the derivative with respect to x of f of g of x, what I would get would be f prime of g of x times the derivative of the inside, g prime of x, right? And, we're using that capital F there, but f prime, you want to keep in mind, f prime is the same as the original function when we are considering anti-differentiation, okay? So we know our chain rule. So in order to prove this, we're going to start with the left side and we're going to end up with the right side. So what I'm going to say is I have the integral of f of g of x, g prime of x, dx. Okay, so I'm integrating this. And that is the same, because of what I wrote up above, this f of g of x times g prime of x is equal to the derivative with respect to x of capital F of g of x, right? So this is equal to d dx of capital F of g of x, and the dx is still there. So integrating a derivative, those are inverse operations. They're going to cancel each other out. So when the integration and the differentiation cancel out, what we're left with here is f of g of x plus c. Because we were integrating, we have that plus c. So now is where we're going to let that u substitution occur. I'm going to say, well, let us let u equal g of x. So what that gives us is f of u plus c. So if I wanted to rewrite this as an integral, right? So that would be the integral of the derivative of u du, which that is the same as just writing the integral of f of u du. So remember, capital F represents the antiderivative, and when I put that prime in there, the derivative of the antiderivative is the original function, little f. And so that is why or how we can use substitution to perform integration of more complex functions or things that look like a composition with the derivative in there as well. So let's do some examples in our next video.